Good morning students. Welcome back to the class for engineering chemistry for textile technologist. This class we are going to discuss about the unit 5, which is conducting polymers, and in this session we are going to discuss about the characteristics of conducting polymers and what does doping do for a normal polymer to make it conducting. Now let us go to the session. Basics of polymers. This is a recap on the basic of polymers. We know polymers are long chain molecules formed by the combination of simple molecular structure termed as monomers, where the repeated molecular weights, repeated molecular units are joined together by means of covalent bonds. And these covalent bonds are very strong bonds which held together the molecular chains, and we also have weak bonds which makes the two polymer chains attached together. We have a weak bond such as van der Waals forces or hydrogen bonding which make the molecular the two polymer chains combined together. Second thing is polymers are mainly they are insulators. One of the example is polyethylene. They act as an insulator. This is one of the important characteristic of a polymer. Also, the variation in crystallization of a polymer and orientation, it results in vast morphologies of the polymers today. So, this is what made an interesting fact for the synthesis of the polymer. And we also have, it has good chemical resistivity. The polymers, they have good chemical resistivity at room temperature itself. And also, it has low density. And a polymer, they have brittleness at low temperatures, and they can be stretched to form films. So these are some of the basics of the polymers. So polymers are long chain molecules. They are insulators. The crystallization and orientation decides the type of the polymer. The chemical resistivity, they have chemical resistivity at room temperature. They have low density, brittleness, as well as they can be stretched to polymer films. And some of the example of organic polymers are, we have, as I have told you, polyethylene is one of the important example where you have N molecules of ethylene. So, you have N molecules of ethylene that is held together. Another example is vinyl chloride. And we also have several examples, polystyrene. All these are organic polymers. Next, we come to the discovery of conducting polymers. Conducting polymers are discovered in 1977 by three scientists, namely Alan Hager, Heidi, and Alan McDermott. So, these three scientists combined together, they discovered conducting polymers, and before that polymers were used as insulators in electronic industries, but only after the discovery it has been used as conducting polymers. So, it finds main application in electronic industries, and it has advantages over conductors also. What are the advantages over conductors? If you see, the first advantage is it is a chemical advantage, mainly ion transport is possible, and it has a redox behavior unlike your conductors, catalytic properties, and electrochemical effects. photoactivity as well as junction effects. So, these are some of the advantages over conducting polymers. If you take mechanical advantages, chemical advantages is what I told now. If you see the mechanical advantages, what are the advantages over conductor is, it has lightweight. All of your polymers, it will be having lightweight, it is flexible, it is non-metallic surface property, so it doesn't easily get hot or something like that. Therefore, these are the mechanical advantages that you could see on the conducting polymers. And if you see what is the conductivity on a polymer particularly, so they become generally the polymers are non-conductive, okay, they are not at all a conductors, but they can become conductors by doping. So, the first point here is they become conducting upon doping. The polymers, they become conducting upon doping. This is the first important point here. The second is they become electronically charged. So, this is the second advantage, electronically charged. These all the polymers, they become electronically charged, and polymer chains, they generate charge carriers. The polymer chains, they generate charge carriers. And concentration of dopant. Here it depends on the concentration of dopant. Whatever dopant that you are adding, the polymer, how the polymer is formed, it depends on the concentration of the dopant. It makes the certain electrons unpaired. And then so they have extended pi orbital system or extended delocalization, we can say. They have extended delocalization, extended pi orbital system. So, these are the characteristics of conductivity. Generally, a polymer, it is not conducting, but on doping, it become conducting, and they become electronically charged, and also they act as charge carriers. Depends on the concentration of the dopant, how much you are adding, the electrons will be unpaired based on the concentration of the dopant that you are adding. Also, your polymer will be having an extended conjugation or extended delocalization. One of the first polymers that was synthesized is polyacetylene. Was the first conducting polymers, it was synthesized first. This was the first synthesized conducting polymer. And what are the conditions for a polymer to become conductive? The first condition is the polymers should have alternating single and double bond. It must be having an alternating single and double bond to become conductive, which we call it as conjugated double bonds. So, it must have conjugated double bonds such as localized sigma orbital and which form strong chemical bonds, and delocalized pi orbital . So, this can be disturbed to form conducting polymers. Okay. So, here we have a localized sigma orbital as well as a pi orbital. So, you need alternating single and double bonds to get conjugation. The second condition is, so this is your first condition. The second condition here is, even though you have a single and conjugated double bond, that is not sufficient, but you have to disturb the pi conjugation. You have to disturb it, you have disturbed the polymer by removing the electrons through oxidation or by inserting them through reduction. Either oxidation or reduction must be carried out here. Now let us see this, see the condition with an example. So what are the conditions? Now we have a molecule like this. You have a carbon atom which is attached to a double bond, and then you have a single bond here. We have another carbon atom, then I have a double bond, a carbon atom, a single bond, again a carbon atom. Actually the double bond length is smaller than that of the single bond. So I have given a polymer chain over here where you can see alternating single and double bond. So I have the hydrogen attached to these carbon atoms, which I am writing like this. The hydrogen atoms are given here. So here you have alternative single and double bonded structure. Where we have the carbon atom, so these are nothing but carbon atoms, and this is your double bond. So in the double bond, this particular bond is a sigma bond, and this particular bond is a pi bond. And what is the role of pi bond? It allows easier delocalization of electrons. And this you have a sigma bond. The sigma bond, it ensures the strength of the chain. This is also a sigma bond, and this sigma bond, it ensures the strength of your polymer chain. So this is the importance of the sigma bond, and this sigma bond is nothing but a single bond, and you have carbon atoms. So you can see this is a polymer chain which has been which can be made conductive. It has alternative single and double bonded structures, as well as the bond conjugation is not enough for the polymer to become conductive. Hence the second condition is the polymer has to be disturbed, the chain has to be disturbed. Okay, either it can be oxidized or reduced. So oxidation or reduction must be carried out, which may be p-doping or n-doping. Through p-doping or n-doping may be carried out to make this polymer chain conductive. So this they can affect the surface when you do the doping. This may affect the surface and bulk structural property of your polymer, that is your color, porosity, volume. All these will be disturbed when you do the doping on a polymer chain. So which is an important concept. Now how this doping is done? Let us see doped conducting polymer. How is it done? Now I am going to talk about p-doping here. The conducting polymer are obtained by exposing a polymer chain to a charge transfer agent, and this may be carried out in a gas or in solution. In a gas phase, this may be carried out in a gas phase or in a solution phase, and this is called as a conducting polymer. So doping is the process by which conductivity of the polymer can be increased by creating a negative or a positive charge on the polymer backbone. You can carry a negative or a positive charge on a polymer backbone by oxidation or reduction. So this is what a conducting, and doping may be of two types. P-doping, I am going to write this P-doping, how it takes place. Let us take polyacetylene. It is done by oxidation process. You have a Lewis acid. You have a Lewis acid here, and doping results in a structure like this, CH(X) plus and A minus. This is p-doped polyacetylene. In this process, the conducting polymer, the polymer is treated with a Lewis acid, and some of the common p-dopants used may be iodine, bromine, your ASF3, PF6, etc. So even naphthylamine can also be used. Naphthylamines can also be used here and for p-doping. Next, coming to n-doping. So n-doping can be done I am going to give the structure. Again, I am taking a polymer like this, which is a similar polymer, polyacetylene. When I make to react this with a Lewis base, when I dope this with a Lewis base, I get a polymer like this, CH, X- and B plus. So, you can see here I get a positive as well as here I get a negative product. So, this involves intrinsically treating, in N-doping this involves intrinsically treating your conducting polymer with a Lewis base, thereby reduction takes place. So, here you have oxidation and here you have reduction, thereby reduction takes place and negative charges on the polymer backbone is retained and end-dopants and you can see positive sign on the other side. And the common end-dopers that is used are lithium, sodium and this calcium, calcium, FeCl3, etc. These are some of the common end-dopants that is used. What are the types of doping agents? Here we have already seen some of the doping agents that have been used for P-doping as well as for N-doping. What are the other types of doping agents that can be used? So, dopants may be classified as neutral dopants, where we have iodine, bromine, ASF2, all these. These are all neutral dopants, all your things that I have told you, iodine, bromine, ASF2, your sodium, potassium, etc. So, all these are neutral dopants. We also have the second category, which is ionic dopants. Ionic dopants are LiClO4, lithium chloride, hypochlorite, FeClO4, your CF3, SO3, Na, all these are ionic dopants. These are some examples for ionic dopants. We also have organic dopants. Lately, we have also been using polymeric dopants. Organic dopants are CF3COOH, CF3SO3Na, the sodium salt. So, this can be used as ionic as well as your organic dopant and your PBUNClO4, etc. So, hypochlorate and all. So, all these you can use as organic dopants. And nowadays, we are also using polymeric dopants. Polymeric dopants such as PVS, PPS, etc. So, all these are polymeric dopants. So, these are some of the dopants that can be used to make a polymer conductive. And what happens when you dope it? I am going to give it as a curve, a plot of conductivity versus doping. When I plot a graph like this, I am going to plot it against a doping level and dopant. So, which is that is dopant in CH unit and your conductivity, which is in per centimeter or a centimeter minus 1. So, here I am giving the 0, 0.1 and I can give this as 0.2 and here I am giving it as conductivity from 100, 200 and so on. So, what happens is you can have a graph, we will be having a graph like this. Up to some point this increases and after that there is leveling down. That is conductivity increases up to a certain doping level. This increases only up to a certain doping level. So, this is our conductivity. So, if you add more and more of dopant, it does not mean that the conductivity will go on increasing. It increases only up to a certain level and then it just standardizes down. So, more and more of dopant will not result in high conductivity. Next, we are moving to types of conduction. We have two types of conduction, intrinsic conduction and extrinsic conductors. Intrinsic conductors are nothing but they conduct electricity in pure form. They conduct electricity in pure form due to the presence of electrons or holes together, and extrinsic conductivity by adding external impurities such as doping. Without doping, there may not be, in extrinsic, without doping, there may not be any conduction that will be taking place. Holes are formed by the removal of electron on doping. Generally, this holes, it is formed by the removal of electrons by means of doping. Okay. What does doping do? What does doping do? What doping does is, there are several types of doping also. The doping are redox doping, which we saw in the previous example, non-redox doping, redox doping is one that we were following, photo doping is also there, and charge injection doping, electrochemical doping. We also have electrochemical doping. So, these are some of the doping types, and what does it do to a polymer is, on oxidation, when oxidized and reduced. If you see into two categories, what happens? An oxidized conducting polymer is more conductive. They are more conductive, whereas this is less conductive, and second, here they have more capacitance. Compared to this, it has less capacitance. This is less transparent, whereas this is more transparent, and this you have less hydrophobic, that is water repellent capacity, and this is expanded, and here you have contracted. The polymer is contracted, and here this is more hydrophobic, and here you have higher modulus, and here you have lower modulus. So, these are the characteristics of a conductive polymer. Conductive polymers are inappropriate oxidized or reduced state conductors due to their unique stretched pi conjugation. They are overlapped pi orbitals, they form a valence bond. It is not a bond, valence band. It forms a valence band, and pi star orbitals, they form a conductive band. They form a conductive band due to chemical or electrochemical oxidation of conductive polymers. The electrons are removed from the valence band, and which leads to the presence of charge on the conductive polymer, which delocalized over several monomer units in the polymer and cause relaxation of the polymer to form a most stable form. Dopants can be incorporated during synthesis of polymer itself to create a conducting polymer. So, the effect of dopant, conductivity, as I have told you through the graph, the conductivity increases up to a certain level, and secondly, the stability decreases, and morphology is due to presence of charges, shape will not be retained. Morphology, shape will not be retained. Retained here. So, this is the effect of dopant. The conductivity increases up to a certain level, the stability decreases, the morphology shape will not be retained. So, doping, you have redox doping, non-redox, photo, charge injection doping, electrochemical doping, and on you can have oxidized and reduced form. If you compare the table properties, I have given it here, and also the pi conjugation is one of the important parameters where you have shift of electrons from valence band to conductive band to oxidation or reduction. And the effect of dopant is given here. Thank you for the session.